Hello friends, today we are going to discuss some introductory part of kinematics and then we will cover some basic definitions that one come across while studying kinematics. So the very first question that arises in our mind is that what does kinematics mean? Kinematics. Kinematics is the branch of mechanics which deals with the motion of objects regardless of the causes producing it. So in kinematics, we study the motion of object without concerning about the causes producing it. And in order to study the state of object, first of all we need to define the frame of reference, and in our case the frame of reference will be the Cartesian coordinates, in which we have x, y and z axis mutually perpendicular, and we have a clock fixed in the origin to measure the time. Now there can be two types of states of an object. The object can be in two states. It can be in rest and either it can be in motion. So how do we define the rest state? If the space coordinates do not change with time with respect to given frame of reference, the state of object is described as rest with respect to that frame of reference. And similarly, motion, if the space coordinates change with time with respect to the given frame of reference, the thing we need to keep in mind is that with respect to the frame of reference, the state of object is described as the motion with respect to that frame of reference. So rest and motion is a relative concept. It is not an absolute concept. For example, we will see that a train which is carrying passenger is moving with some velocity v in right direction, and in another case we have a passenger standing on the platform. Say this is the passenger who is standing on the platform, say name this passenger A, and the train is also moving in rightward direction. So in the first case, the passengers inside the train feel that the train is at rest with respect to them, because passengers are also moving with the same velocity. So the train is at rest with respect to these passengers who are inside the train. Now when we analyze the state of the train with respect to the passengers A standing on the platform, we find that the train is moving rightward with velocity v. So the train is at rest for passengers inside the train, but the same train is in motion for the passengers standing on the platform. So rest and motion is a relative concept. Without the observer, the rest and motion has no meaning. So now we will move to some basic definitions. So now we will define the position and position vectors. Position of any object in a given frame of reference is defined as the coordinates in that frame. Say object is at A, has coordinates, say coordinates xa, ya and za. And similarly, the object at B has coordinates xb, yb and zb. So the position of point A will be defined by the coordinates in that frame of reference, and position of point B will be described by the coordinates of B in that frame of reference. So now how do we define the position vector? The position vector is defined as the vector joining origin to the point we are interested in. Say position vector of A Say if a object at A has position vector, a vector pointing towards A starting from origin. So say, let's say it is RA. The position vector of A is defined as RA, and we write it as XA I cap plus XB J cap. Oh, sorry, it should be X. No, it should be Y. YA J cap plus ZA K cap. Similarly, we can define the position vector of any object at B. If I say it is RB, the position vector of B in a given reference frame, similarly I can define RB as XB I cap plus YB J cap plus ZB K cap. Now, in order to define the position vector of B relative to A, what I mean is I need to find out RAB, the position vector of B with respect to A. What is it? RAB. Now in triangle ABO, if I apply the triangular rule of addition of vectors, what I find is OA plus AB is equal to resultant, that is OB, from vector addition. Vector addition rule. So what is OA? We have OA as RA plus AB. We have defined it to be RAB. It has to be equal to OB, and OB we have defined as RB. Hence, we get RAB, the position vector of B with respect to A, as RB minus R. So it is the change in position vector of B from A, that is the subtraction of position vector of B minus position vector of A. So we have seen that how to define position vector. Now we move to the definition of distance and displacement. So distance is the actual path of length traveled by a body in moving from one point to another. Say the initial position of particle was A and final position was B. So the actual path traveled by body is through A, C, D, B curve. So distance will be length of curve A, C, D, B. Now displacement is defined as the shortest distance between the final position and initial position of object. So in our case, the final position is B, initial position is A. So what can be the shortest possible path between point A and A? That can be the line joining A and B. So we can write displacement as length of line AB. And from here we can see that displacement can never be greater than distance. So distance is always greater than or equal to displacement. And when distance can be equal to displacement? When the actual path traveled by body is along the straight line. So in that condition, AB will be is equal to the distance traveled by body in moving from A point to B. So let's see some another definitions. Average speed and instantaneous speed. The average speed of a particle in a time interval is defined as the distance traveled by the particle divided by the total time interval. It means, say, distance traveled by body in time t be say delta s. If delta is the distance traveled by a body in time interval delta t, then average speed is defined as, say, v. Average speed will be defined as, if I write it as average speed, it will be defined as the ratio of length of path covered divided by time taken. So this is the way we define average speed, the ratio of distance divided by the time interval. So now let's see what is instantaneous speed. So it is defined for a particular instant. So from average speed we have seen that average speed is displacement divided by interval during which the particle traveled delta s distance. So now when delta t tending to 0 and delta s by delta t is finite, then it is defined as instantaneous speed. We say v, I just write it down as v. So by default instantaneous speed is written as v. So it will be equal to, v will be equal to ds by dt. And pictorially we will see in subsequent slide how does it come out to be the derivative of distance with respect to time. So instantaneous speed is defined as derivative of displacement with respect to time at that particular instant t. So now we will see graphically how it comes up to be. So in this case, instead of s, we are studying the motion of particle along x direction. So this is the distance. Say this is the distance along x direction in our case, and this is the time along x direction, along x axis, and along y axis we have the distance in x direction. So now we see if the actual path traveled by a body is along a red curve, this red curve, and initial position was p and final position was q at time t2. So how we have defined the average velocity? We have defined average velocity as the change, the distance traveled. So what is the distance traveled? If initial position was x1, final position is x2, what is the distance traveled by body? x2 minus x1, because along y axis I have distance, so it will be x2 minus x1, the distance traveled upon the time taken, that is t2 minus t1. T2 minus t1. So it is analogous to or either I can write it as del x by del t. So now when delta t tend to 0, so in that case point Q gets closer to point B. So in average speed, it is the tangent of the chord which is average speed. But in instantaneous speed, in the case of instantaneous speed, we see that V is the tangent at the curve of distance versus displacement. So it is the tangent at point P when Q gets closer to P and when delta t tend to 0. So in that case it will be tangent to the distance versus time curve. So I can write it as delta x by delta t, and delta t tend to 0, it becomes tangent to the distance versus time curve, which will be dx by dt. Or because in this case we were studying the motion along x direction, and we can generalize it as ds by dt. It will be instantaneous speed. So now let's move to some more definitions: average velocity and instantaneous velocity. So the average velocity of a particle in a given time interval t is defined as its displacement divided by the time interval. Say the displacement covered by a body be delta r. Say it is delta r, or I can write it as a to b, that is position vector of rb minus position vector of ra. So this is the change in the position vector, which is displacement, and if it happens to be in the time interval of delta t, that is t2 minus t1. So how do we define average velocity? Average velocity is defined as rb minus ra upon t2 minus t1, that is change in displacement upon change in time. So this is the way we define average velocity. Now we see the instantaneous velocity. The instantaneous velocity of a particle is also defined for a particular instant t, just like instantaneous speed. So in that case we can write it as v, velocity vector, as the derivative of displacement curve with respect to time, and its explanation is quite analogous to what we have seen for instantaneous speed. So now we will see what is average acceleration. The average acceleration is defined as change in velocity divided by change in time. If initial velocity of particle, was say v I at time t, and final velocity of particle was vf at time t2. So if initial time was t1, So average velocity is defined, average acceleration is defined as change in velocity divided by the time interval. So we can write it down as acceleration average. Because it's a vector, we should put a vector sign as equal to final velocity minus, so we can put a vector sign, we minus initial velocity upon the time interval. Or analog, or equivalently we can write it as change in velocity vector divided by time interval. So this is the way we define average acceleration, change in velocity vector divided by time interval. So now let's see how do we define the instantaneous acceleration. The approach is analogous to what we have seen for instantaneous speed and velocity. The instantaneous acceleration of a particle is also defined for any particular instant t. So in the case of average acceleration, what we have seen is it is delta v divided by delta t. But when delta t tend to 0, then it becomes equal to the derivative of velocity with respect to time in the curve of velocity versus time. And I just designate instantaneous acceleration as a. So whenever we talk about acceleration velocity, it means it is average instantaneous velocity or instantaneous acceleration. So I am not just putting the subscript for instantaneous. By default it is instantaneous acceleration. So in this case, del v by del t is a finite quantity when delta t tend to 0, and that finite quantity is equal to the instantaneous acceleration. Or I can write it down as a is equal to, which is instantaneous acceleration, as derivative of velocity with respect to time. So this is instantaneous acceleration. Thank you for your attention.